Welcome to Cosmos Explorer. I'm Dr. Eugene. In a groundbreaking discovery, the James Webb Space Telescope has directly captured a supermassive binary star system in the distant universe. This incredible achievement just hit the Astrophysical Journal and is sending shockwaves through the American Astronomical Society. Let's dive into what makes this so extraordinary. In the universe, which was born approximately 13.8 billion years ago, the formation and evolution of stars have played a crucial role in determining its entire history. When the universe was first born, it was almost entirely composed of the lightest element, hydrogen, and the next lightest, helium. Elements that surround us today, such as carbon, oxygen, and iron, barely existed in the universe at this point. However, as the universe expanded and temperatures dropped, gravity began to pull gas together, eventually leading to the birth of the first stars. Inside these stars, temperatures and pressures became incredibly high, igniting nuclear fusion. During nuclear fusion, lighter elements combine to create heavier ones, which are then scattered into space when massive stars evolve and explode. These elements, released from stars, diffuse into space, promoting the formation of new matter. Eventually, gas containing these elements is gathered once again by gravity, giving birth to second and third generation stars. Because these new generations of stars are richer in heavy elements than previous ones, they can give rise to more complex and diverse celestial bodies. As this cycle of stellar birth and death was repeated over and over, heavy elements gradually accumulated in the universe. These elements enable the formation of diverse stars and beautiful galaxies, and even serve as the building blocks for rocky planets. When planets like Earth are formed, they become rich in elements essential for life, such as carbon, oxygen, phosphorus, and sulfur, ultimately leading to the emergence of life like us. Considering this evolution of the universe, it is necessary to investigate in detail how stars are born, how they evolve, and how they affect their surrounding environment. In particular, recent studies have revealed that about 70% of massive stars existing from the early universe to the present day have evolved as binary systems. This means that throughout the history of the universe, many stars have not evolved in isolation, but rather while exchanging matter and gravitationally interacting with a neighboring star. Therefore, to understand stellar evolution in a way that reflects reality, we must consider not only single stars, but also how they mutually influence each other as binary systems. So, what kind of life cycle do interacting binary stars actually follow? The presence of a companion star brings about decisive changes at every stage, from a star's growth to its final moments. This diagram illustrates the diverse evolutionary paths of binary stars. In a binary system, the heavier star usually depletes its fuel first and swells up significantly at an early stage, making it easier for its outer gas to enter the region strongly influenced by the companion's gravity. As a result, gas flows into the companion star, altering the mass ratio and the width of their orbit, which even dictates the star's lifespans and how they meet their end. Then, when the heavier star reaches its final stage, its core collapses, triggering a supernova explosion. Consequently, an extremely small and massive object, like a neutron star or a black hole, is born, while the outer layers of gas are blown away into space. At this time, the gravitational balance that maintained the binary system changes abruptly, so the system either remains a binary after the explosion, or it becomes unbound. If it remains as a binary system, it continues to evolve, sometimes leading to the merger of two neutron stars, or two black holes. These mergers are observed as gamma ray bursts, or they emit gravitational waves. Therefore, the evolution of binary systems is tied to various astronomical phenomena, and we need to carefully unravel this evolutionary process. To unravel the complex evolutionary processes that such binary stars follow, we must not only rely on theoretical calculations, but also individually observe stars existing in the distant universe to directly confirm their true nature. In astronomical observations, looking at distant galaxies and stars means going back in time to when the light was emitted, essentially looking directly into the past. In other words, capturing distant stars provides a very important clue to understanding how stars existed in the universe when it was still young. However, capturing a single shining star within a galaxy 10 billion light-years away is no easy task, even with the state-of-the-art James Webb Space Telescope. Because the distance is so vast, even if the galaxy itself is faintly visible, the individual stars within it become buried in the surrounding light, making them impossible to distinguish. This is where gravitational lensing, which acts as a natural magnifying glass, plays a crucial role. Gravitational lensing is a phenomenon explained by Einstein's general theory of relativity. When a massive celestial body is present, its influence warps space-time. Light from a background object passes through this warped space-time, changing its path of travel. This result is observed as the gravitational lensing effect. The strength of this effect depends on the mass distribution of the lens object, as well as the positional relationship between the background object, the lens object, and the observer. The mass, or weight, dictates the strength of the lensing effect. The heavier the object, the stronger the effect. Additionally, the effect also changes depending on the positional alignment of the celestial bodies. When the background object, the lens object, and the observer align in a straight line, the effect is at its strongest, and the observed background object forms a characteristic ring structure known as an Einstein ring. In fact, Earendel, the most distant candidate for a single star discovered to date, was also found because its light was amplified thousands of times by a powerful gravitational lens created by a galaxy cluster, the largest type of structure in the universe. What looks like a red streak is a distant galaxy, stretched and magnified by gravitational lensing. The dot-like feature visible within it is Earendel, the candidate for the most distant star existing inside that galaxy. Whether this object is a single star remains a subject of ongoing debate, but it demonstrates that the gravitational lensing effect is a powerful tool that complements human technology, allowing us to see far into the distant universe. Furthermore, a phenomenon that can push the power of this gravitational lens to its absolute limit is gravitational microlensing. This is a phenomenon where, instead of a massive cluster of galaxies, small objects within it, such as individual stars or black holes, act as the lens. The greatest feature of microlensing is that, because celestial bodies are moving through space, the lensing effect changes over time. The moment the lens object crosses in front of a background star along our line of sight, the light intensifies dramatically and then returns to normal once it passes. By utilizing this temporary brightening, we can reveal the existence of distant stars that would normally be too dim to see, or even compact objects that emit no light at all. In fact, in the nearby universe, the microlensing effect is observed like this. The horizontal axis represents time, and the vertical axis represents magnitude, indicating brightness. Data acquired by various telescopes is shown. It captures how the brightness changes rapidly as a massive object passes in front of a background object. Recently, a research team led by Dr. Hayley Williams of the University of Minnesota used the James Webb Space Telescope to find a peculiar point-like light source within a distant galaxy called the Warhol Arc, located behind the galaxy cluster MAX J0416.1-2403. The redshift of this galaxy is determined to be 0.94, which means it has captured the state of the universe from approximately 7.7 billion years ago, or roughly 8 billion years ago. The discovered light source was named W2, and through 4 separate observations, it was found that not only its brightness, but also its color was changing. 8 different filters were used for the observations, and the changes in its light were carefully tracked over a period of 126 days. As a result, it was discovered that in addition to the gravitational lensing effect caused by the galaxy cluster, a compact object was inducing a microlensing effect, further magnifying W2. What is important about this discovery is that it didn't just become brighter. W2 showed varying appearances of its red-looking and blue-looking components, depending on the time of observation. This diagram shows the spectrum illustrating the actual color changes. The horizontal axis is wavelength, and the vertical axis is brightness. Spectra observed 4 times at different periods are shown. During the first observation, it appeared blue, but in the second observation, the red component became brighter, and in the third observation, the blue also became brighter. Then, in the fourth observation, the blue component became even brighter. To explain this behavior, the research team hypothesized that it was not a single star, but rather a binary star system. If only one star were brightening on its own, its color would not change. Therefore, by assuming that 2 stars, one cool and one hot, are positioned together, it becomes possible to explain not only the changes in brightness, but also the changes in color. Based on this, the research team drew up the following picture. The white vertical line in the left diagram indicates the region experiencing the lensing effect. The binary system is assumed to consist of a cool, giant red star and a hot, compact blue star. Because they form a binary system, the 2 stars are in slightly different positions. Each star orbits around a specific common point, so their positions change over time. Therefore, the way they experience amplification from microlensing changes over time. For example, if the blue star moves closer to a high magnification region, the overall color will appear bluer. In fact, looking at the changes in magnification determined by the research team, it looks like this. The horizontal axis is time, and the vertical axis is magnification. As a result of this analysis, the research team concluded that a model with 2 components, a cool star at about 3,500 Kelvin and a hot star at about 12,600 Kelvin, fits best. In other words, it indicates the possibility of a pairing between a large red star, like a red supergiant, and a hot blue star, like a B-type star. Furthermore, to distinguish whether this light source is truly a single binary-like object or a small star cluster, the research team placed limits on the physical size of the source. By using information on how long the microlensing brightening lasted, we can estimate the extent of the glowing region. As a result, they found that the size of W2 is, at most, roughly 90 astronomical units or less. While this is larger than the distance from the Sun to Pluto, it is far too small to be a star cluster. So what does this binary star system look like? The research team compared large-scale theoretical calculations of binary star evolution with their observational results to find a combination that could reproduce W2. As a result, the most plausible scenario is a massive binary system pairing a red supergiant with a hot main sequence star, with each mass estimated to be roughly 21 to 24 times that of the Sun. Also, the mass ratio when the binary system formed was close to 1, suggesting a high probability that the 2 stars were born with very similar weights. The orbital spread is also most likely in the range of a few to several tens of astronomical units, which was found to be consistent with the size limits established in this study. What makes this interpretation important is that this binary system is at a quite unique stage of evolution. Depending on the conditions, there's a possibility that we are observing a stage where one of the stars is nearing the end of its life as a red supergiant, close to the moment just before it triggers a supernova. This means that this observation not only captured the image of a massive binary system in the distant universe, but also might be peaking at the very scene just before it proceeds to a massive explosion. What is particularly important about this discovery is that an era is beginning where we can individually study the stars themselves within distant galaxies, even including the possibility of them being binary systems. Until now, the condition of stars in the distant universe could only be estimated from the average light of the entire galaxy. However, By utilizing a natural magnifying glass created by the universe, as done this time, we can close in on the true image of massive stars that lived in the universe roughly 8 billion years ago. If observations like this increase, we will be able to directly trace throughout the history of the universe what percentage of massive stars were born as binaries and how they evolve in supernovae and black hole binary systems. And this is a tremendous step forward in understanding the origin of heavy elements, supernova explosions, and furthermore, the population of celestial bodies that will emit gravitational waves in the future. I look forward to seeing future developments. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.